The universe is filled with an unthinkable number of stars, with each cosmic giant varying greatly in size and appearance. But how did they get there, and what will happen to them? Across billions of years, stars go through incredible transformations, shaping the universe as we know it. So let's see how stars live, grow, and ultimately die. Stellar evolution begins with the formation of a star. How does a star form? A star begins forming when a triggering event, such as supernova shock waves, causes a part of an interstellar dust cloud, such as the one shown in the picture, to begin contracting under its own gravitational force. This is stage 1. In stage 2, one of the individual cloud fragments continues to collapse. The interior of this fragment has heated to 10,000 Kelvin by stage 3, and by stage 4, a protostar forms. At the protostar stage, the developing star has formed into a spherical shape, but is not yet a star because nuclear fusion has not yet begun. Protostars are large, bright, and cool. Planetary formation has begun, but the protostar has not yet reached equilibrium. At stage 6, the core reaches 10 million Kelvin, and nuclear fusion finally begins, meaning the protostar is now a star. What is nuclear fusion? Nuclear fusion is when extremely hot nuclei overcome their repulsive forces to fuse into one singular, heavy nucleus. In a star's core, hydrogen atoms are fusing to become helium nuclei, releasing a significant amount of energy that powers a star. At stage 7, the star has reached equilibrium and is now in the main sequence of the HR diagram, where it will spend 90% of its lifetime. As shown in the picture, the main sequence is the long band through the middle of the diagram, which includes most of the stars, including the Sun. Our Sun has been in the main sequence for about 4.6 billion years and is theoretically predicted to spend another 5 billion years on it. Stars will stay on the main sequence until they run out of fuel and can no longer fuse hydrogen into helium. When this happens, the star begins to lose equilibrium. Its structure rapidly changes, and the star leaves the main sequence, marking the beginning of its end. The end of a star's life depends on its mass. First, I will discuss the death of a Sun-like star, or a star with a mass similar to that of the Sun. After about 10 billion years, a Sun-like star runs out of fuel. Nuclear burning ceases, weakening the star's pressure and disrupting its equilibrium, causing the helium core to begin contracting. Because fusing helium requires a temperature of 10 to the 8 Kelvin, as compared to the 10 to the 7 Kelvin temperature required to fuse hydrogen, the star's core is not hot enough to generate energy through fusion. Even after 10 billion years, the star is still mostly made up of hydrogen, yet it is all gone at the core. The shrinkage of the core releases gravitational energy that heats up the shell layers outside the core in a process called hydrogen shell burning. The star's surface temperature has dropped while the luminosity has slightly increased, putting the star at the subgiant stage. The path taken by the star from the main sequence to the subgiant stage can be tracked on the subgiant branch in the HR diagram, as shown in the picture. At this point, the Sun-like star has reached 3 times the Sun's radius. As the core continues shrinking, the star's temperature remains nearly constant between stages 8 and 9 of the HR diagram. The star follows the red giant branch, as shown in the picture, until it reaches stage 9 and is a red giant. By stage 9, hydrogen shell burning has caused the red giant's luminosity to increase to hundreds of times that of our Sun, with a radius of 100 times larger than the Sun. That being said, about 25% of the giant's mass is packed into a core slightly bigger than the Earth, meaning the core is extremely dense. A few hundred million years after the Sun-like star leaves the main sequence, temperatures at the core have reached 10 to the 8 Kelvin, and helium begins to burn in the core. The pressure remains unchanged, more or less, as the nuclear reaction rates increase and the temperature rises rapidly in a helium flash. A helium flash is a brief but intense event where helium in the core fuses rapidly, causing the temperature to rise so high that the core can no longer degenerate, causing it to expand rapidly. The core expands and equilibrium is restored as the core begins to fuse helium into carbon in a process called the triple alpha process. After the helium flash, the star jumps from stage 9 to 10 on the HR diagram, where the temperature has increased but the luminosity has decreased. Helium depletes and a non-burning carbon core begins contracting. By stage 11, the star is again a swollen red giant, following the asymptotic giant branch in its second giant phase. Luminosity and temperature have greatly increased. The star then reaches stage 12, where the core can no longer contract. Beyond the carbon ash core is an expanding cloud of dust and gas, producing a planetary nebula, one of the most beautiful cosmic phenomenons in the universe. After a few tens of thousands of years, the expanding cloud fades and cools, dispersing into interstellar space, and the planetary nebula disappears from view. The dense, hot, and small carbon core remains, no longer concealed and now called a white dwarf. This is stage 13 of the HR diagram. White dwarfs reside in the bottom left of the diagram. The white dwarf no longer undergoes nuclear fusion, so it cools off for billions of years, eventually dimming into stage 14, a black dwarf, a dead star at the bottom of the HR diagram. This marks the end of a sun-like star's life. But what about a star much more massive than the sun? High-mass stars have a much shorter lifetime than low-mass stars, meaning they evolve much faster and die much more dramatically. High-mass stars experience much more ravenous fuel consumption and spend a shorter time on the main sequence. While a sun-like star will spend 10 billion years in the main sequence, larger stars may only spend 100 million years on it. Larger stars take different paths on their way to a giant, as shown in the HR diagram with stars of 1, 4, and 10 solar masses. These stars reach 10 to the 8 Kelvin while still close to the main sequence, much quicker than sun-like stars. A massive star burns helium smoothly with no helium flash, and the star remains a red giant while fusing helium into carbon. The massive star moves back and forth near the top of the HR diagram as shown. The star's radius increases as the temperature drops, and it swells into a red supergiant. The star eventually dies in an extremely large and violent explosion called a supernova. If the star's mass was not high enough to form a black hole, the core will collapse into a neutron star. Neutron stars are only about 12 miles wide in diameter, but are so incredibly dense that they have a mass greater than the sun. If a star is massive enough, the supernova explosion will leave behind a black hole, a region where gravity is so incredibly strong that nothing, not even light, can escape. What about a small mass star? Small mass stars can have lifespans of trillions of years, far exceeding the current age of the universe, meaning they evolve much slower than sun-like stars. They burn their hydrogen at a much slower rate, and their red giant phase is much smaller and less dramatic than that of a star similar in mass than the sun. Low-mass stars end their life as a smaller, less luminous white dwarf, also eventually cooling down to a black dwarf.